I want to start by saying that I was very fortunate to start working with Dan about 5 years ago. So this have been like great 5 years of my life. I've learned a tremendous amount of mathematics from Dan. And we had a joint student, Kent Vashaw. And Kent and I today will try to present some of the work that we came up with in these past years. And before I switch to that work, I wanted to come up with a request. So before request for Dan. So on your birthday, you get requests too, not just birthday presents. So my request is like long before we started working together, like I've read many of your papers, they have had a huge impact on many mathematicians like me. And it was set the day that you were hired here in order to publish 5 very strong papers every year. So my request is, so please continue doing this for the next 30 years. All right. So the only thing is, I don't know, like, how do I switch? Now it works. All right. So the setting of the talk will be about monoidal triangulated categories. And luckily, we already saw several very interesting examples of these categories today. So first of all, these are triangulated categories. They are over algebraically closed field K, no assumptions on the characteristic of the field. We have a tensor product, which is assumed to be bi-exact and associative, and we have an identity object one. So first, a couple of other things. So such a category is called braided, and if we have a natural isomorphism between the usual order of the tensor product and the reverse order of the tensor product. And the category is called symmetric. If you compose that with itself, gives you the identity natural isomorphism on the tensor product. So we had several examples today, and I want to come back. The first thing the last talk in the morning was Charlotte's talk, and she was stating this remarkable theorem about isomorphism between 2 triangulated categories with natural tensor structures. So when you work in algebraic geometry, very often you have monoidal triangulated categories which are intrinsically symmetric. We also had another example of a symmetric monoidal triangulated category that came up in John's talk. If G is a finite group, we can look at the representations of G over a field K. Then this is a Frobenius category, and we can look at the corresponding stable category where we kill the morphisms to projective injectives. It gives us a triangulated category with an induced tensor structure because the original tensor structure was symmetric. This will be symmetric as well. We can go one step further, a finite dimensional coalgebra. We can look at the modulus of the finite dimensional coalgebra over the corresponding base field. It's again a Frobenius category. It's well known that finite dimensional coalgebra is self-injective, so the corresponding representation category will be Frobenius. Again, we can look at the stable category, but now this gadget is very rarely braided. It's not symmetric. It's very rarely even braided. For instance, it will be braided when the coalgebra is quasi-triangular. There are very important examples when this thing happens, like the small quantum group, for instance. But there are also like lots of finite dimensional coalgebras for which we want to study the corresponding representations, and we have nothing commutative about the tensor structure on this triangulated category. And the focal point in my talk today would be on finite tensor categories. So this is some very natural generalizations of module categories of finite dimensional coalgebras, and people care a lot about this in relation to representation theory, mathematical physics, and quantum computing, topological quantum computing. So finite tensor category, now this is abelian. This is in the abelian level. It's a abelian K-linear monoidal category. First, the finiteness means that there are finitely many simple objects. Every object has finite length, finite Jordan-Felder series, and the home space is a finite dimensional, and also there are enough projectors. So when you look at these 2 conditions, they simply mean that this is the module category of a finite dimensional algebra. But that finite dimensional algebra does not have to be a Hopf algebra. So we insist that there is a tensor structure which is bilinear on spaces of morphisms. We insist that every object should have left and right dual, whatever this means. Like we can imagine like some natural axioms in terms of evaluation, co-evaluation maps. And that the endomorphism ring of the identity object is simply is reduced to the base field. Right. So just like I said, these are coming up in various sort of situations. The term finite refers to the first two assumptions. The finitely many simples and enough projectives. And a very quick consequence of the existence of inverses is that you can write down left and right adjoint functors for the left and right tensor products, which gives you immediately that the tensor product is bi-exact. A similar trick similarly gives that F is Frobenius, so you can look at the corresponding stable category, and it's a monoidal triangulated category again. And there are interesting examples of these gadgets that are symmetric and are not coming from finite group schemes. So already, even at this level, when you don't have a Hopf algebra around, you get lots of new examples. So these are the kind of things that we want to study. This is the focal point. And intrinsically, this gadget is not symmetric and it's not braided. So in some way, we will see that it behaves both in a commutative and a non-commutative fashion. So that's somehow like the remarkable part of this theory, that intrinsically we start with something that looks like a non-commutative algebra on a triangulated categorical level, but it has lots of commutative features behind it. All right. So now that we have all these nice examples, I want to come to this problem that has been approached like it's a problem of sort of very high interest already in the 80s. For different versions of monoidal triangulated categories, people were looking at how they can classify the thick ideals. And a thick ideal by definition is a triangulated category, full triangulated category, which is thick, which means closed under direct summons. It's an ideal, it's closed under left and right tensoring. And we want to come up with some sort of framework to classify this. And Paul Balmer made a fundamental contribution to this by developing the subject of non-commutative, the subject of tensor triangular geometry, which was a way to basically approach this problem in a unified way instead of sort of a case-by-case basis. So I will just formulate a few of the building blocks of Paul's theory. There are many different layers of this theory. So first, he associates a topological space to this category. The points are the prime ideals, and the prime thick ideals are simply thick ideals that have the usual commutative primeness property. So if the tensor product of two objects A, B is in P, then at least one of them should be in P. And then this is equipped with a certain topology that looks like sort of the opposite to what you would do in the Zariski topology. And this is the Balmer spectrum of the corresponding category. And like I said, like there are many different layers of what you can do with this. You can make this into a locally ring space. You can produce a sheaf, a pre-sheaf of categories on these things. So this is basically the starting point of non-commutative of tensor triangular geometry. Now this thing, I should formulate now Paul's theorem. So Paul's theorem is that if you have a symmetric monoidal triangulated category K, then there is an order-preserving bijection between the radical thick ideals. This is what we wanted to classify, and the collection of Thomason subsets, the spectrum of K. And Thomason subset means that it's a union of closed subsets with the property that the complement of each of them is quasi-compact. If you knew that the SPC of K is a Noetherian topological space, then instead of working with Thomason subsets, you could work with specialization closed subsets, which are just infinite unions, possibly infinite unions of closed subsets. Okay, so here is this fundamental theorem of Balmer, but lots of the categories that we want to deal with are intrinsically non-commutative. They're not symmetric, they're not even braided. So we have to have a sort of a version of something like this that would allow us to basically deal with various sorts of support theory for these other categories that are intrinsically non-commutative. And the first step is recalling non-commutative ring theory. So I think that there is sort of a dichotomy. Some people like non-commutative ring theory. Some people feel that it's an area that goes very much isolated from the rest of mathematics. So I don't know like which of the two groups of people you fall. Maybe there is an intersection. But I mean, they were supposed to be mutually exclusive statements, but maybe maybe there is an intersection between A and non-A. All right, so non-commutative ring theory. So if you have a ring R, you say that an ideal is prime if it has the property that the product of two ideals ij is in P implies that at least one of them is in this is a type. It's either I is in P or J is in P. So the R here should be P. So equivalently, you can say that if all possible products A times R times B happen to be in P, then at least one of A and B are in P. And the usual notion that we know for an ideal, for a prime ideal, that's what's called completely prime ideal. And people have very long discovered in non-commutative algebra that this second property is not a good problem. So take, for instance, n by n matrices, the ring of n by n matrices over a field. If you were considering only the second kind of ideals, there will be none. But if you consider the first kind of ideals, then 0 would be a prime ideal. So that's why you really want the first. And then this is something that Henning Krause told us. So he told us that he thinks that the very first paper that appeared on the Balmer spectrum was actually this paper that they wrote, and it was a non-commutative generalization of the Balmer spectrum. This is what Henning thinks, that it's the very first paper after Paul's paper on Balmer spectrum. So same thing, so you just translate everything from ring theory to categories. A prime ideal is an ideal that behaves like that with respect to peak ideals. And then the non-commutative Balmer spectrum of K is the collection of prime, again with the same kind of topology like in the original work of Paul. So at this stage, we have like a really nice object that we hope is doing something. And at the same time, we are thinking, wait a minute, like, was it really worth like just jumping and generalizing everything from ring theory to categories? Is it really going to work? So the first theorem that I want to show that is that actually it works. So if K is a rigid monoidal triangulated category, we assume that it's generated by a single object as a thick subcategory. So for example, you can think about finite tensor categories. So finite tensor categories have finitely many simple objects. Take the direct sum of those objects. Look at the corresponding object in the stable category. It's going to generate it as a triangulated category. So this condition that is generated by a single object is satisfied in very broad generality. Then there is a bijection between the thick ideals and again the Thomason subsets of the spectrum of K. So in other words, what Paul was able to prove in the commutative world, we can extend this fully to the non-commutative world. The assumption that the category is generated by a single object is essential. So we have to do lots of arguments that go around the commutativity, so we cannot drop that one. Rigid means that every object has left and right inverse. That's not an important assumption. So if the rigidity is I think it was too close. So if the rigidity is dropped, then the bijection is simply between the non-commutative versions of prime ideals, which are called semi-prime ideals. And the whole theorem works in that situation. And then finally, I want to say that if we assume that the spectrum of K is, the SPC of K is Noetherian, so that's what I mentioned, that in that situation, Thomason subsets would be the same thing as specialization flow subsets. Then in that situation, the theorem was proved also by James Rowe. All right, so now that we have this problem of classifying thick ideals, and we see that the topological space behind that is the non-commutative Balmer spectrum, we want to come back to the question of how that relates to classical support theory, which is support theory through cohomological support. So for the rest of my talk, I want to jump into the problem of how the non-commutative Balmer spectrum in general is related to cohomological support in general. What can we do? So the answer is this much we can do, but I want to spend 45 minutes talking about it. All right. So let's go over the basic setting. So we're having a finite tensor category in the background. So this is the module category. It's an abelian category, which is the module category of a finite dimensional algebra. We have a biexact tensor product. Every object is dualizable, left and right. The endomorphism algebra of identities is reduced to scalars. It's a Frobenius category, and we can look at the corresponding stable category, which is a monoidal triangulated category. So in this setting, we have the non-commutative Balmer spectrum, which was introduced before, the one that goes with a stable category. And we have something that we will call universal support. On the next line, it will become clear why it's universal support. So it's a map from the objects of our triangulated category to the closed subsets. So chi closed denotes the closed subsets of the topological space SPCFT, where the support of A is all prime ideals, thick prime ideals that do not contain A. And it has this non-commutative tensor product property. So this somehow never sort of really appeared before. What everybody was always concerned with is whether a support map will have the tensor product property, which is same identity like this one, but without X in the middle and without union in the left-hand side. Just that the support of M tensor N with the intersection of M and N. So since we're in the non-commutative world, this universal support has this kind of tensor product property. And the statement is that it's actually a universal terminal object in the category of all support maps with this property. So every other support map can be pushed down to this. All right, so this is on one side. This is the side that comes from the non-commutative version of Paul's theory. So now let's go back to the classical side, which existed for way longer. So it was pioneered by Quillen. This is cohomological support of finite groups and generalizations to pop algebras and so on and so forth. And then many people contributed to it. In particular, John Carlson has some very, very fundamental contributions to this. And later we will come back to further things about this kind of support. All right, so we're looking at the cohomology ring of a finite tensor category T. So by definition, the cohomology ring of a finite tensor category is the X algebra of the identity object. So this is the actual definition of the cohomology ring. By very simple trick, it's actually isomorphic to the Hom spaces in the triangulated category between the 1 and the positive shifts of 1. And the corresponding product can be described in terms of composition and tensor product. And this is a graded commutative ring. If we have two objects A and B, then we can look at the corresponding extended Hom space, where again we sum up the Hom spaces for all shifts from 0 to infinity. So this is canonically a bimodule over the corresponding cohomology. So we can look at the support of this bimodule. So the support of that bimodule is the cohomological support. So this is a map from the objects in our triangulated category to the closed subsets of the prof of this ring. It's a graded commutative ring that's positively graded. And the support of an object A consists of all prime ideals that have the property that they contain the annihilator of the corresponding model. So by defining support in terms of containment of annihilator, we avoid the condition that your module has to be finitely generated. So instead of localization, definition in terms of localization, like the definition in terms of inclusion avoids any finite generation assumption at this stage. At some point, of course, finite generation will come up. Now, the definition in terms of triangulated category also had the really nice advantage that instead of taking the sum over k greater or equal than 0, we can take the sum over all k. And that's going to naturally give us the Tate cohomological support. So we define the Tate cohomology ring of a finite tensor category to be simply the Hom in T between 1 and all possible positive and negative shifts of 1. And then if we look at the corresponding Hom spaces between A and all possible shifts of B, that's going to become a bimodule. So we define the support in exactly the same way like before. And then it's going to give us a map. I have a typo here from the objects in T to the closed subsets of the homogeneous spectrum of R hat. So I'm just missing here the closed subsets of this topological space. All right, so now we can ask the question, what's the relationship between the spectrum of the stable category of T and the Prosh of the cohomology ring of T? Respectively, we can ask the question, what's the relationship between the spectrum of the Balmer spectrum of the stable quotient of T and homogeneous spec of R hat of the Tate cohomology ring? Not only we have topological spaces, but we also have corresponding support maps. So we can continue the question, what's the relationship between the corresponding support maps? So on one hand, we have the universal support, and on the other hand, we have the cohomological support. I started dropping here closed subsets here, since it's kind of understood. And on the Tate side, we still have the universal support, and we have the Tate cohomological support. So perfectly nice question, what's the relationship between three topological spaces here and 3 support maps here? Now, there are some very fundamental theorems that settle this in some extremely important situations. And this theorem said that basically there's homeomorphisms. These things are exactly the same. So the first in the case of finite groups, this was very heavily based on John Carlson's rank support varieties, which established that the cohomological support has the tensor product property, and out of it, it was proved that these two things are homeomorphic. And in the case of finite group schemes, this is a fundamental result of Friedlander and Websolver, which is based on their important notion of pi support. So we have these things that work for finite groups and finite group schemes. And of course, we feel very happy here, and we're like, yes, let's jump and prove this. And for some other situations, and it's kind of very hard. So this is really hard. Even you pick up a finite dimensional Hopf algebra just at random, and you're basically stuck with this theorem or with this problem. Now it's even worse. If T is not braided, there are known cases where the 2 cohomological supports are completely different. So there was a paper of Benson and Witherspoon about 8 years ago that said that basically the 2 things are very much not related. They're just really different. So the first thing that I want to present here is a notion that we give a categorical center of cohomological ring and of cohomology ring. And we think that somehow this is the notion that's going to provide the bridge between the 2 things. But before I jump to describe exactly like the definition, I want to remind everyone that the cohomology ring is already graded commutative. So we're not picking up the center of a graded commutative ring, which will be again the graded commutative ring. That would have been a very nice notion, but not much luck with that other notion. We tried it very much, but we did not succeed to pick up the center of a commutative ring. So now this is a portion of the cohomology ring that in some way commutes with objects. The beauty of categories compared to rings is that there's so few things you can do with rings. You have only elements of your rings, and you can multiply and add them. But in a category, you have objects, you have morphisms, and you can just play with all these kind of things. So that's exactly where this center can work. So let's take a morphism from 1 in a shift of 1, and we will say that that is in the categorical center if the following thing happens. So first, the object 1 is canonically isomorphic to 1 tensor M and M tensor 1. So this is just the definition of the identity object. The shift of M is also canonically isomorphic to the shift of 1 tensor M and M tensor the shift of 1. So the bottom lines are all isomorphisms, the top lines are all isomorphisms. So if I have an element which is in the home space between 1 and the shift of 1, I have the vertical arrow on the left and the vertical arrow on the 1. And we say that this G is going to be in the categorical center if this diagram commutes for all simple objects M. And this is the definition of the categorical center of the cohomology ring of R. So this was on the Tate level, and then you can go down to the non-Tate level simply by looking at the case when n is greater or equal to 0. Perfect. So first, if T is symmetric or more generally braided, you don't change anything. So good news, we didn't kill our cohomology ring, make it smaller in situations where we should not make it smaller. So in the situations where it should stay the same, it stays the same. Now next comes a diagram that I want to tell you that this kind of center is related to two other kinds of centers. So if you're in the world of tensor categories, a billion world of tensor categories, one thing that you do all the time is Drinfeld center. So I'll tell you that now this is related to the Drinfeld center. On the other hand, if you're doing triangulated categories, then you're doing something that's called the graded center. So then I'll tell you that it's also related to the graded center. So somehow this center sits between the Drinfeld center and the graded center. So first of all, this is the world of tensor categories on the billion level. So C here is a monoidal category, and the Drinfeld center of a monoidal category is a braided monoidal category. The elements are objects A together with a natural isomorphism. It's natural with respect to X here, so A is fixed. The variable is X, so it's natural in X. It's called half braiding because it's half. The object A is already fixed, so you're only braiding X around A. And this is supposed to satisfy certain natural assumptions. So this center was introduced around 1990 by Drinfeld and Majid, and it's playing a fundamental role in tensor categories. And here's an example. If you look at the module category of a Hopf algebra H, then the Drinfeld center of that is precisely the module category of the Drinfeld double of the Hopf algebra. So it produces something really interesting. And then the next theorem is that the center of a finite tensor category is a braided finite tensor category. So now we have the forgetful functor from the Drinfeld center of T to T. And this is a functor on the abelian level. It's an exact functor on the abelian level. So this now is going to descend to a functor on the triangulated level from the stable category of the Drinfeld center of T to the stable category of T. So now I can go back to the picture and explain what the picture means. Since we have a functor from the Drinfeld center of T to T, and that functor exists on the triangulated level, we have a functor, we have a homomorphism from the cohomology ring of the Drinfeld center of T, the cohomology ring of T. So the statement is that the categorical center that we produced is actually includes the image of this homomorphism. So in other words, our categorical center is definitely bigger than the dream field center. So this is sort of the first moment. It's okay. We did not produce something very small. We can control whatever we produce from below because it definitely contains the dream field center. So we have a lower bound of how small things. So remember that we have a big cohomology ring R, and we're producing something central inside. Would have been horrible if you produce something really small. There's nothing you can do with that. So the first news is that it's not small, it's big enough, it contains the dream field center. Okay, so now the next thing that I want to explain is that it actually can be viewed in a very natural way as equalizer in terms of the graded center. So if you have a triangulated category, so here is special, but this works for any triangulated category, then the graded center of this triangulated category by definition is the graded commutative algebra that consists of all natural transformations from the identity functor to the powers of the shift functor that skew commute with the powers of the shift functor. Okay, this is the graded center. We don't assume anything monoidal here, but if we have a monoidal structure, then we have two natural embeddings of our cohomology ring in the graded center. One is by mapping M to the shift of M, where you do the tensoring on the left, and the other is when you do the tensoring on the right. So now if we compare the definition, then our center was precisely the equalizer for these two maps. So in terms of this graded center, we also have like a very natural way to think about this new center. It's just the equalizer of these two homomorphisms. All right. And I want to come back to what John talked in the morning, the groups of endotrivial objects. So now we want to think like, how can we think conceptually about this categorical center of the cohomology ring? So we think that this is some sort of generalization of fixed point subrings. I want to try to persuade you now that this is a sort of a very natural generalization of, I have an algebra and all that I did was introduce some notion that generalizes fixed point subring. Okay, so if M is an element in T is called endotrivial, exactly like in John's talk, if on the triangulated level, M tensor M becomes identity. This is certainly not the case on the abelian level, because that tensor product can never be identity. It can be, but in super rare cases. So then the message is that in very many situations, this cohomology ring is nothing but the fixed point subring. The categorical center is nothing but the fixed point subring of the categorical of the cohomology ring. So let's look at one example here. So this is what's called Balmer-Witherspoon-Hopf algebras. So we're having a finite group L that acts on a finite dimensional Hopf algebra A. So then what we do is we take the dual of A, we take smash product with the group algebra of A, we dualize one more time, and we produce something that as an algebra looks like A tensor, the coordinate ring of L. But it has a very twisted structure. This somehow came up in work of Benson and Witherspoon, and it was basically declared to be an example that says that the Balmer spectrum and the cohomological support will not talk nicely to each other. All right, so now in this situation, we can prove that the categorical center of this new Hopf algebra is precisely the same thing as the fixed point subring of the categorical center of the original Hopf algebra. And now if we look at the special case when A is actually the group algebra of G, this is precisely the Benson-Witherspoon Hopf algebra, then we see exactly the phenomenon that we had on top of the slide, is that the categorical center is precisely the fixed point subring of the cohomology. So there it is. So this is how we want to think about the categorical center. It is something that generalizes fixed point subring. The whole ring is like module finite over its center. So this is the kind of thing that we want to think about what's going on here. And there is another very important example, coordinate rings of finite group schemes. So I mentioned the work of Eric and Julia about finite group schemes. So this is the dual one, the coordinate rings of that. And I will mention more about this. But if we look at the coordinate ring of a finite group scheme, it's actually a very special case of this Plumnik-Witherspoon algebras, where the things that we're having around is the corresponding infinitesimal group scheme and the corresponding finite group. And if we're in this situation, then the cohomological, the categorical center is precisely the fixed point subring under pi of the coordinate ring of the infinitesimal group scheme. So again, we want to think that this categorical center is something that generalizes this kind of formulas. All right. So the last piece of information that I want to provide before jumping to theorems is about finite generation. So this is like a very big topic. It's certainly something that's somehow fundamental in many respects. So the Eppingo-Ostrich conjecture is that if you take any finite tensor category T and you look at the corresponding cohomology ring, it's finitely generated. And if you take any element M in the finite tensor category, then the corresponding extended endomorphism ring, which is a module over the cohomology ring, is a finitely generated module. So people really believe that this should be true. Like there are really absolutely no counterexamples to this. And Julia is smiling. I think she would say, like, why do you think something is true? Because there are no counterexamples. Right. So first is the fundamental work of Friedlander and Suslin for finite group schemes. This is true. So this is a real tour de force work, where you manage to prove that something is finitely generated without computing it. So this is really like important part of that work. It's based on axiomatics, not on concrete structure theory. Then there were many works after that where for classes of Hopf algebras these things were proved. But in these are very important works. For instance, there is a very recent major work of Andruszkiewicz and Giono, Julia, and Witherspoon, where they prove this for pointed Hopf algebras that come from Nichols algebras of diagonal type. But the thing that one has to say about these other works is that for the Hopf algebras, for the classes of Hopf algebras for which one can prove this conjecture, we're still doing something that pretty much computes the cohomology rather than proves at once that it's finitely generated. So somehow it's still up in the air. What would be there? What would be the method up there that would actually prove finite generation without getting to the structure of the cohomology? So that's still very open even for Hopf algebras. Even more for finite tensor characters. So there are some hopes, and it's still very open even in the braided case. So just take a braided finite dimensional Hopf algebra, still completely open whether the corresponding cohomology ring is finitely generated. And now I want to introduce a notion of weak finite generation, and that's going to enter in our theorems. And the weak finite generation says that if you look at the extended endomorphism ring of an object, it has to be finitely generated over the categorical center. And before, when I gave this talk, I mean, this is like the 50th time I give this talk, so I'm very bored. So before, when I give this talk, people immediately say, but this was categorical center, so it sits inside the cohomology ring. You say that it's a weak finite generation, but it looks like you're making a stronger assumption that your module is actually finitely generated over a subalgebra rather than the actual algebra. In what sense it's a weak finite generation? It's a strong finite generation. You assume more than what they want to conjecture. So the note then is that finite generation for the Drinfeld center implies weak finite generation for T. So not only we're making a weaker assumption, but we're only basically assuming everything would follow from the braided case. So if tomorrow somebody proves finite generation for the braided case, braided Hopf algebra, that will be already enough. So we won't need for other algebras. Okay, and similarly, we can give a Tate version of finite generation. So exactly the same thing in the Tate picture. All right, so next comes a theorem, which is inspired by another theorem of Paul. So once we somehow started working on this, we started reading Paul's paper, and we were like, now we have to think about the second paper of Paul, and then about the third paper of Paul. Anyway, so in one of his papers, Paul managed to produce a map from the spectrum of monoidal triangulated category to the product of the corresponding categorical ring. But now we will do that with the categorical center. So now the key point is that we get rid of the cohomology ring here. It's not the right object. The cohomology ring is simply way too big in general. What really plays a role is the categorical center of the cohomology ring. That's the gadget that enters the picture. All right, so we can produce a continuous map from the first topological space to the second topological space that's given by a certain formula. And it's also it's also compatible with the two support maps in the sense that the inverse image of one is contained in the other. We wish this to be equality, but in generality like this, you simply can't prove it. Okay, if T satisfies quick finite generation, then rho is surjective. So we already have here a situation where we can say something about this map, and the only thing that we assume is only weak finite generation. So the cohomology ring could be absolutely infinitely generated algebra. The only thing that we need to assume is that a certain module is a finitely generated module. Okay, and then there's similar statements on the corresponding Tate level. All right, so now I want to pause for a moment. So before, when people said that if you want to classify thick ideals of a certain category, then that's done in terms of Balmer spectrum, and people essentially proved that the Balmer spectrum is homeomorphic to the product of the cohomology, and this was done all in one paper. So we don't think that this would be something. We don't think that somehow one would be able in one paper to basically go for every finite tensor category from one topological space to another. It's just like, it's one of those things where it's great that it worked in a certain situation, but you pick up a random Hopf algebra and there's very little you can say about this. All right, so conjecture is that for every finite tensor category, this map is actually a homeomorphism. And then completely separately on the right-hand side, we actually have the product of the cohomology ring. So when people thought that there is basically no relationship between the product of the cohomology ring and the Balmer spectrum, the answer is yes, there is no relationship, but there is actually a homeomorphism to the categorical center, and then one can reconstruct one from the other. So we should imagine that basically there is another map that goes from the categorical center is a subalgebra of the cohomology ring. So we get a certain map that goes in the opposite direction from the product of the cohomology ring to the categorical center. So we believe that this is a homeomorphism and for finite tensor category, and we think that it's going to take ages to actually prove this. It looks hard. It just looks hard even for like you pick up some 16-dimensional Hopf algebra and go ahead and prove this. So, all right. So now I want to list a couple of theorems that say that something works, but then we keep adding more and more conditions, and we keep getting less and less satisfied because there are more and more conditions. So we were kind of satisfied with the first theorem that we have very few conditions. Now in this next theorems, we think that this is not the way to go. We think that somehow what we have to do is basically come back and analyze the situation in this full generality. We have this map and start thinking about the fibers, what we can say about the fibers. We know that it's a surjective map, but but we can start studying the fibers. So that's what one should do, and that we cannot do at this point. At this point is we can throw more assumptions and improve something under those more assumptions. So the next theorem is to produce a right inverse. In order to produce a right inverse, we need to assume that the central cohomological support have the non-commutative tensor product property. This is known in some situations, but it's hard thing even for a finite quantum group. Even in that situation, this is still wrong. So if we throw this assumption, then we know that there exists a map like this because we said that the non-commutative Balmer spectrum is universal terminal object. So we definitely have a map that goes in this direction. It's actually given by this formula. And what we can prove about this map is that if we compose rho and eta in this order, so eta is sitting on the right, then the composition rho eta becomes a contraction. So it shrinks the ideals. Right, and we want that to be equality. And it's one of those things that, I mean, you really want to make that equality, but in order to make it equality, you have to add a condition. So if this satisfies weak finite generation, up to this point, there was no weak finite generation. This is the very first point where we have finite. So if this satisfies weak finite generation, we can produce a right inverse. So that contraction map becomes actually equality. So this is producing the right inverse. And then you are like, yes, let's prove now that eta is actually a left inverse. And that's exactly what we wanted to do. So let's prove that eta is a left inverse. And again, same problem. So eta times rho applied to any p is actually contained in p. It's again some sort of contraction. So the opposite composition is again some sort of contraction. And there's nowhere to go around. You can make that work. We can make that become equality. Not simply a composition that's contraction, but you have to throw other properties. And I will try to be very quick about this. So let me just flash this quickly because somehow it's becoming a little more technical. So in order to basically to force the last identity to become the last composition to become identity, we need to use Ricard's localization and co-localization functors. In order to do that, we need to work with a category that has arbitrary coproducts. The way to do that is to take our finite tensor category to look at the incompletion. The incompletion is Frobenius. That's not difficult to prove, so we can look at the corresponding stable category of the incompletion. This is now a triangulated category that has arbitrary coproducts, and the stable category of T is the compact part of this. So we need to assume that our support actually has an extension to the incompletion with this property. And if that is the case, then eta and rho are actually inverse homomorphisms. So I have 1 minute, and in this 1 minute, I want to basically give these examples. So recall that the Plumnik-Witherspoon smash product Hopf algebra is to start with a Hopf algebra A with an action of a finite group and to produce a new one that is some sort of a skewed version of the original one. So the theorem that we can prove is that even though the last theorem was kind of unsatisfactory, if all conditions are satisfied for the Hopf algebra A, then all conditions will be satisfied for the Hopf algebra AL. And in particular, if we work with the Benson-Witherspoon Hopf algebra, then the Balmer spectrum of the Benson-Witherspoon Hopf algebra is precisely the Prosh of the cohomological center, and the cohomological center becomes the fixed point subring. So originally in the work of Benson and Witherspoon, they had something like this, but they were like, wait a minute, there is absolutely no relationship between this ring and the original cohomology ring. So somehow the two objects look completely different. So what we managed to achieve with this categorical center is that now everything non-commutative is completely on equal footing with everything commutative. It's just instead of with the cohomology ring, you work with the categorical center of the cohomology. Same thing for finite group schemes, if you look at the corresponding coordinate rings of finite group schemes, again, the theorem is that the Balmer spectrum on the left side is precisely the same thing as the Prosh of the categorical center. The categorical center happens to be, in both cases, 6-point subrings. So this is a theorem that Chris, Negron, and Julia proved 2 years before us. Like they proved this using hypersurface support. The point that we want to make now is that all this fits into one general framework where on one side you have the Prosh of the categorical center, and on the other side you have the non-commutative tensor triangular geometry. So I want to finish with wishing Dan a very happy birthday and asking him to continue writing 5 very strong papers every year.
Any questions? So the cohomology ring, the Univ, basically the Univ ring, which doesn't depend on the tensor structure.
That's right. Yes.
And of course, you choose, you don't have, without tensor structure, the one doesn't make any sense, but if you choose anything,
that's right.
Product, which is still a ring.
Yes.
So in this finite case, how heavily ring would affect the commutativity, including the center of the tensor structure was
this thing that you mentioned actually entered very heavily in the theorem that we proved over here. We needed a certain result about the categorical center over here, and we looked at the representations of the coordinate rings of the finite group schemes. If you forget the tensor product structure, that becomes the same as representations of a finite group, and you can use results about representations of a finite group. So that enters very essentially. But when we talk about the categorical center now, we really very heavily use the tensor product, because it's a certain thing that you cannot define with the tensor product. So you're very right. That's a point it's actually very heavily used in the field. Like lots of other people, like I think this also enters in a very important way in Eric and Julia's works, like that. You can play with forgetting the tensor product, doing some things, and then coming back.
The section that eats out the comparison that captures the close point, right, from this inclusion. Yeah. So from this inequality there, lines before the end, you guess that theta catches all the close points, right?
Exactly. Yes, exactly.
Does it also catch the middle point, the generic point?
I have to think about that. I have to think. Thank you. That's a very good question. I have to think about that. So somehow, like we spent a lot of time about somehow analyzing the fibers. So this is at this point where we don't have finite generation, so we're not sure that our map is surjective. And I think something can be said, but I have to think about it. This is definitely the way one should go, basically. Start analyzing this map without any additional assumptions. Yeah.
Instead of how the theory, you can capture those points.
Yes, exactly. This is exactly how we envision. Like we want to basically bring the locally ring structure. We want to bring the sheaves of categories here and basically analyze everything. So that's definitely the way to go. Yeah.